it creates one of these structures in the kernel. It just allocates memory for this structure and then it inputs it. So somewhere in the kernel you will find this key structure here. And there's 2 or 3 different things that I find very interesting. First you have this character array here with the file name. And then you have a character array with a crypto name. And then we have the key. And all of them are a fixed size. So for instance here, the file name and the crypto name has this LO name size. And I think it's like 128 characters or something. And then following straight after it, we have the encryption key and the crypto key size. This makes it very, very easy to search for this in memory. We have to know 2 things. Either we have to know the name of the encryptor, or we have to know the name of the file. So if we actually have gotten this far as to actually extract someone's memory and trying to search for the crypto key in memory, we probably know which crypto he is using, or we know the file name of the file we're trying to break into. So it's highly likely that we will be able to search for this. So in this example, I've created a memory dump using Xen. I just saved the memory of a running machine into a file, and then I did open it in a hex editor. And I know this is really fine print for you guys in the back, but here we can see the file name. So it's root secret stuff, and in hex. And then we have the algorithm of choice here, 2fish. So if I either know the encryption key, the file name, or the encryption algorithm used, I can use this to search for the length of the file, or the entire memory file. And here you can see the very, very secret key, my secret key. And as I said before, there are different versions of util Linux out there and LO setup, and this one doesn't hash the key. So here you can read the key in plain text. It will pad it up to the required size with null bytes, and at the end here we have the encryption key length 20. That's 32 bytes, 256-bit keys, and this is a really, really bad way to handle keys. But as I said before, the default version that is included in util Linux behaves this way. So, what if we have, for instance, Debian instead? Debian chooses to hash the key, or rather hash your password into a key of the specific length. Here we have another example, the name loop file. It's a bit shorter, so it might be harder to find, but if we know the name, we can search for it. The same with AES. It's a very short string, so if you search all of the memory for AES, you're going to end up with like 1 billion hits. But since we know that it will be null padded up to the fixed length, we can search for AES and then a lot of null pads. So it's actually quite easy to search for as well, because in a function name or in a variable name or something like that, it will not be null padded. So since we know how long it is, we also know where the key starts. So even if the key started with a null, we would still know where it starts because of the fixed length. So here we have a binary key, and it ends with the encryption key length. So it knows it ends with 20 always, or of course it could be 128 bits as well, but that's not very common. It could also be 192 bits, I believe. Anyhow, since we know where it starts, we know how long it is. So this one is hashed, which makes it a bit more troublesome if you have the wrong LO setup to use. But let's start with how to reuse the key for clear text. When you're using CryptoLoop, reusing a clear text key is very simple. You just input a clear text key. We doesn't have to bother with the length of the key or anything because it's always null padded. So we simply use the LO setup tool -e 2fish loop 0 and the data loop file that we want to go into. I believe my example is wrong here because it was named secret file or something. Anyhow, we just input a password, my secret key, and we can use, for instance, tune to FS or something to check that we actually got a file system there that is working correctly. So it's basically very, very, very simple to use. So then we come to the binary keys. The binary keys are a lot harder to use. UtLinux, as it comes by default, has a fence post off by 1 bug. For one reason or another, they choose to always put in a null byte on the last character. So even if you input a full 32 byte as your key, it will always truncate it and input a 0 at the end. So if we have a key that is hashed, for instance, by Debian, and we have it in a binary file, and we input it to LOSetup as a string and say, please don't hash this, I want to use this as my key, it will truncate it, and the end byte will always be 0. So this might be interesting as well, because you think you're using a 256-bit key, but you're actually using a 248-bit key, because the last 8 bits are always 0. And this makes it very, very difficult for us to input a key that is actually 256 bits. So it's virtually impossible. We have another problem as well. We're using string copy. A string copy doesn't like certain characters, for instance, null. So we're not going to be able to input a key that contains null in it. But in this example, I have patched my LOSetup to allow for 32-byte keys, and I have a crypto key that doesn't actually contain nulls. So in this case, I'll be able to use like Perl or whatever hex editor you like to input your key into a file, and I can like just cat it and pipe it into LOSetup, because it has the P0 option to identify a file descriptor to read a key from. This isn't the only option available to us, because as I said earlier, dmcrypt is compatible to certain lengths with Cryptoloop. So we could actually use dmcrypt that uses hex keys as well. But it's difficult to input this kind of key using the stock LOSetup. And even if you have a patched version from, instance, Debian or Ubuntu that actually does hash the key, you don't want to hash the key, you want to use the -n flag or something to tell it not to hash the key. And then it will revoke and go into this xstring copy function that is actually very, very broken. And you will end up with a truncated key anyway. To handle a key, a binary key as a string, causes other problems as well. We can't have certain characters in it. We can't have line feed, for instance. We can't have null in it. And there's a whole bunch of other characters that we can't use either, because it's going to be interpreted by my shell or my keyboard or the kernel or the string copy function or whatever. So Cryptoloop being keyed by UtLinux is actually broken from the beginning. But we can input our hashed or binary key once we've extracted it, and then we can access the data. And as I said before, finding the actual key is as simple as loading your memory dump into a hex editor and just doing a plain text search for the crypto or the file name. So it's very, very, very simple. So let's have a look at dmcrypt, because it's a bit more trickier. It was introduced in the 2.5 or 2.6 series kernel. It uses the crypto API, as does recent versions of Cryptoloop as well. It's intended to be a replacement for Cryptoloop. As I said before, there's been different versions of Cryptoloop. The LoopOS author has a lot to say about the security of Cryptoloop, and dmcrypt is partially compatible with Cryptoloop. And if you've read about the problems, or like there's a plain text fingerprinting attack on Cryptoloop, this is also valid for dmcrypt, since they are compatible at a block level. They actually have the same type of problems. But they have introduced some kind of IV segmenting thingy to try to solve that. But if you have a file with a known fingerprint in it on your Cryptoloop, the bad guys will be able to find it. They won't be able to decrypt it, but they know that it is there. So if you have this pirated movie or something. Anyhow, it uses the crypto API, and it is supposed to replace Cryptoloop. So keying. The keys are introduced to the kernel by an IOCTL, and dmcrypt is part of the devmapper infrastructure in the Linux kernel. So it uses the libdev mapper, which is like a common framework for talking to the device mapper. And there are 3 different solutions for keying. We can use DM setup, which is kind of awkward to use, but it gives us like a raw interface into libdev mapper and the IOCTLs used, so we can set up different kinds of cryptographic solutions. We have crypt setup, which is very, very easy to use. It has a good mount page, and I believe most people would prefer to use crypt setup. And then we have crypt setup LUKS, and LUKS stands for Linux Unified Key Setup, or something similar to that. And LUKS actually creates a small header at the start of your cryptographic partition in order to be able to save information about your crypto, like your key length and your IV and perhaps your cryptographic algorithm of choice and the size of the partition and stuff like that. So there's a small little header up there. This actually makes it very easy for the user, but it also makes it easy for the forensic officer trying to find your encrypted partition. So from a security perspective, I would never recommend anyone using the LUKS setup unless you're like stupid and don't know how to use DM setup or crypt setup, because it's going to be really, really easy to find it. And then I don't even have to guess your encryption algorithm because it's going to be documented in the LUKS setup. DMCrypt uses hexadecimal keys for keying, so we don't have any problem with the null bytes or stuff like that. So it's very easy to extract and reuse the keys in that sense. So this is going to be really hard to read, but this is the crypt config, which is the struct used by DMCrypt to hold your encryption information and encryption key. And if you compare this to the structure we had for CryptoLoop, we can see that there are no character arrays here, so there's no easy thing to search for. All we have are a lot of pointers and some fixed values, and then at the bottom we have the crypto key, which is just an empty character array that will contain the key. So from this we can conclude that there's no easy way to find this, even if you know the file name, even if you know the encryption. But on the other hand, we know that right after this struct will be the key. So how do we find the key? Well, we know that we have kernel pointers, and we know that the kernel memory is always located in the same place. So I've created an if statement that verifies if all of these pointers has a value above 0xC00000 something, because we know that all the kernel memory will be resided there. And also we have some fixed value stuff. We have the key size. It will probably be 16 or 32. It could be 192 as well, but anyway. And then we have the IV offset, which should be 0 always. There's well, there are a few cases where you want to use another offset, but most people will use 0. I had a friend who actually tried this on his computer, and it turns out the IVGen private is not always a kernel pointer. Sometimes it's just a value. I don't know why, but I could update the software later on. The program to do this is included in my paper, and the paper is available on the website, so if you want to try this at home, please do. So if I have a memory dump and I run this program, it will simply output the key in hexadecimal form. So it will search the entire length of your memory dump byte by byte and compare it to this if statement, and if it's true, it will print the key. Very, very simple. No magic at all. So how do we reuse the keys? So we have a memory dump, we got the key, we have it in hexadecimal form, and we want to reuse it. First of all, DMCrypt doesn't actually work with files at all. It works with devices. That's one of the main differences. So in order to access a file as a device, we have to set up a LO setup first. So we loopback mount our secret file on dev loop 0. Then we use the blockdev command to get the size of the device,